Alrighty. So this is kind of a recap of the stuff that I finished up last time, and also I wanted to throw in stuff about polynomials, kind of. Number one, R is an integral domain if and only if the power series. This is the exact analog polynomial, so it's the same sort of results true. R is a domain if and only if the polynomial rings. Units diverge quite differently from power series. We'll talk about that in a moment. I'll give you some specific stuff. The units, if R is an integral domain, so I have to throw in domain here. If R is a domain, then the units of the polynomial ring and the coefficient ring are exactly the same. However, for power series, it's more exotic. Power series, to be a unit of power series, all you need is for the constant term to be a unit. In particular, if you ever see a power series that's got a constant term 1, it's a unit. There. If you have an ideal in R, then I power X, and this, remember, this notation just means power series, all of these coefficients for I in R power X is an ideal as well. And the exact same thing is true for polynomials. For power series, if you have an ideal, then R power X mod I power X is R mod I power X. This is exactly the same for polynomials again. And you've had this one homework exercise. And so from this and from some earlier stuff that we have, I is prime if and only I is a prime ideal of R, if and only if this is a prime ideal R power X, if and only if this is a prime ideal of R power X. And the same analog is true for polynomials. I and R is prime if and only if IX is prime ideal of RX, if and only if I comma X is prime ideal of RX. And finally, there's one more kind of major, if you will, divergence. And actually the fact that this is different from polynomials is very intimately related to the fact that this is different from polynomials. A maximal ideal in the power series ring is always of the form m comma x for some maximal ideal of R. Right? In the polynomial case, if you have an ideal that is of this form, then it's a maximal ideal. But not all maximal ideals are of that form. So let me give you a couple of examples and illustrate this. But any questions on that there and what it's saying? Okay. So example. Suppose I've got a field. This is kind of an easy example to think of. So suppose I have a maximal ideal of a field. What does a maximal ideal of a field look like?
Well, one it's basically an ideal that if you have any other ideal that contains it, then it'll basically be either be in itself or the ring or if it F, you know?
Right. And so that limits your choices because of the fact that I'm assuming it's a field.
Probably all the one that's non-units.
Okay. What are the non-units of the field?
Probably, well, zero the buzzer.
Zero only, right? Because everything that's not zero is a unit. So let me tell you what a maximal ideal looks like in a field. That's it, right? Notice the ideal generated by X and f of x is maximal ideal, right? Basically, the ideal generated by x is it's every polynomial that has a factor of x in it, right? So in other words, it's every polynomial whose constant term is 0, right? How can we prove that this is a maximal ideal? Well, there's a couple of ways. Let's prove this in a couple of ways, perhaps. Suppose there's a bigger ideal, right? Then there has to be something in N that has a non-zero constant term. Do I agree with that? So there exists, let's say, g of x in N such that it's 0, and I'll call it so. Do I agree with that? So let's write g of x. And remember, the sample is in N. Now notice that A is g of x minus x times b1 plus b2 x plus bn x n minus 1. I agree with that? Because really, all I'm writing here is g of x is this thing, and then pull off that. And notice that this is in the ideal generated by x, which is contained in N. And this is in N. So A is an N. Can somebody tell me what's wrong with that?
Well, here's the point. A is either 0 or it's one of the units, because f is a field.
Okay. So, one, therefore, N holds all it holds. So this is maximal ideal. Let me give you an alternate. And this one's convenient too. Oh, it's alternate proof. B from fx f and so here's the way this homomorphism works. My input is some polynomial, and my output is what you get when you plug in 0 of that polynomial. It's easy to check that this is a homomorphism. And in fact, in all that, it's actually onto, right? Because take your favorite element of the field, call it alpha. Alpha alpha is also a polynomial. When I plug in 0 to a constant polynomial alpha, I get alpha back, right? What is the kernel of this homomorphism?
Appears to be the entirety of f(x).
No, not all of that, right? For example, 1's not the kernel. This is the set of all polynomials such that 0 is 0. Agree? What does that mean about the constant?
Oh, it's like it's set generated by.
Constant term has to be 0, right? And notice every single polynomial in this set is divisible by x. You can pull an x out. This is the ideal generated by x. So fx modulo the ideal generated by x is isomorphic to f. This means the ideal generated by x is maximal. Because when I mod it out f of x by this ideal, I get a field. That means that has to be a maximal ideal. So that's an alternate proof. Everybody okay with it? Now notice, now that I've gone through the steps to sort of justify that this is the case, notice that x remember 0 is maximal ideal of field f. So this is just like the power series from 0 comma f, right? However, the ideal period by x plus 1 is also maximal. In fact, let's go back to this. Just go back to this approach to showing it's maximal as well. And instead of plugging in 0, plug in -1, right? This will also give you a surjective homomorphism in the kernel will be the ideal term by x plus 1. But the ideal generated by x plus 1 is not it's clearly not this form, right? Because there can be no x in an ideal that contains x plus 1 if it's proper. Because if you've got x and you've got x plus 1 as well, then you have 1, right? And by the way, there's only one maximum here. So, like I said, any ideal of this form for commutative ring of identity, maximal comma x, that'll be a maximal ideal. But unfortunately for polynomials, that's not the only one. In fact, with a field, you look at a polynomial ring over a field, only one of the maximal ideals is of that form the power series always stays on. And there are always infinitely many maximal ideals. So most of them are not of that form. Let me give you one more kind of contrast. I mentioned this last time, but I want to kind of reiterate it a little bit. Related to the contrast between unit behavior uh, between Rx and R power X. All you need for be a unit in R power X is to begin with the unit, right? You're coming from the unit. Here it's much more complicated. Well, seemingly simple first. The unit groups of the polynomial ring and coefficient ring are the same as far as the integral domain. Anybody want to guess what happens with zero divisors? That gets a little trickier, actually. So you might think about this just for fun. More generally, so I didn't record this result before. This is a form of current down. What is the form of the general unit of polynomial? Well, just like algebra, you just got to have a unit constant term, right? That's even true there. It's just the difference here is it can't have any other terms other than the unit constant term. For this, you can. Where these NIs, if you want to guess what the NIs have to be. Good. So as far as an integral domain, I'll be in the middle of zero when you get to the result. So there you go. The units for power series are kind of strange. How many of you remember this when you first started doing Taylor series in calculus, right? I remember that. Of course, they'd always have those crazy analysts. They'd always have the disclaimer: absolute value of X less than 1, right? These are just formal symbols, and we don't have to worry about that too much here. You ever remember ever doing stuff like this? You'd have to figure out the Taylor series here. So this is 1 over times, right? Now you can replace every X by 3X. And so from this, you can capture, this thing is really the inverse of 1 minus 3X, right? And you could do other crazy crap like this. There's another exotic one that you would do probably in calculus. Let's do that one. Okay. And then I'll leave that 1/2 out front for later. And then I'll use the series replacing every well, so I'll read this. Now I'm going to replace X by minus X over 2. This is going to be 1 minus x over 2 plus x squared over 4 minus x cubed over 8. You can do this kind of stuff over and over again. Minus 1, I guess, n, x n, or 2n. And this thing is essentially the inverse of 2 plus x. Everybody okay with that? Why does this work in general? Now, I would call this kind of a heuristic demonstration. This is not really a proof. You'd have to go through the inductively build the order, but let me kind of show you. Suppose you have a power series. I'm going to call this high school division, right? This is a bit silly, but I'm going to really. Now, why would a power series getting in a unit be a unit? Well, you basically got to be able to divide this into 1, right? And get a power series. The first thing I get to balance things out is 1 over u. So that's 1 plus a1 over u x plus a2 over u squared, a2 over u x squared plus a3 over u x cubed. My first term has to be that. Great. And now, long division subtract. Oh, there's an X there. Now I've got to divide u into this. All right. What term belongs here? Well, we make this be an a1 over ux. I'm going to need an x there. I guess that's right. That's going to be a1 over ux. Then it's going to be minus a1 squared u squared x squared. It's going to be minus a1 a2 over u squared x cubed, etc. And once again, subtract this minus this is 0 from this point, right? And then you get this weird x squared term. It's like this minus this. So it's a1 squared over u squared minus a2 over u x squared. And then some other yang that I don't want to write down at all. Right? But the key is, why can you keep doing this? Well, there's 2 reasons. Number one, you've got to divide u into this, right? And this is an element of the ring, because even though I know we've got u's in the denominator, that's okay because u's are units and they can go in the denominator. U is a unit, so that divides into whatever's going to be barked out in front of the next term, right? So no matter what, let's see, I guess I just got multiplied by u. So the next term will be like plus a1 squared over u minus a2 over u squared x squared, right? I'm always going to be able to divide a u into the next term because it's a unit, right? And also, it's a power series. So I never have to get that perfect termination with, like you do with polynomials. Since I can go on forever, that creates the quotient that I have. That's very intuitive, but that's essentially how it works. Yes?
when you're writing u in the denominator, we're still not working in like a localization, we're just.
You don't need to, because use the unit, it's got an inverse.
Right, okay.
So you can think of my fraction is, instead of, for example, right here, you can think of this as A1 U inverse. If you will.
Okay.
Okay. Any questions on that? All right. Well, I think this is a good time to segue into the last chapter for talk about something that's near and dear to my heart, factorization. So, yeah, this is probably my favorite chapter.
Yeah, that's
Maybe
what
our president's least favorite chapter. That's okay. Factorization. Okay. What this is predicated on, there is an old theorem that you all probably know. Actually, I'm kind of curious when you all learn this. You all know under the fancy name, the Fundamental Theorem of Arithmetic, right? And basically what that says is if you have any, the most primitive statement of it is if you have any natural number that is 2 or greater, it can be written uniquely as a product of primes, right?
Yeah.
So are you all encountered that in your practice? Am I
Yes,
correct?
I am.
When did you first encounter it, by the way?
Man, probably as soon as I discovered that prime factorization existed.
Well, when did you discover that?
All around ninth grade or so.
Okay.
So,
Yeah. Actually, I was a product of the new math. I mean, nobody understood it, but I think they told us what primes were like at an earlier grade, which is surprising.
Yeah, probably been was seventh grade, but I guess I don't remember. Like I know that every single intuitively that every single number grew into.
What I remember is, and I came up with a theorem actually because a prime was defined. First time I saw a definition in grade school, prime is defined as a number whose only factors are itself and one. Right, so you've heard this. Right?
Yeah, I have.
And then after that, it's like, well, it turns out that every integer 2 or greater can be written as a. Well, actually, I don't even think of that specific. Say, oh, integers that aren't 0 can be written as part of primes uniquely. So in successive years, I asked the following question: is 1 a prime? Right. And I quickly was able to, well, not quickly, it took about 2 or 3 years, and I was able to conjecture a theorem based on the answers I got. And in Tennessee, apparently 1 is prime in an odd number here, and is not prime in an even number here, right? Because that's kind of the answer I would get. Is it prime or not? And the answer is, if you believe in the fundamental theorem of arithmetic, I guess it can't be canon, right? Because if you say that something factors uniquely, well, the easiest thing I got, well, how about 6? 2 times 3. And that's the only way to move from R to prime, right? But if you allow 1 to be prime, wouldn't that also be 2 times 3 times 1? And 2 times 3 times 1 times 1, and so forth and so on. So 1 is really not a prime. This is why we made distinctions earlier when I talked about prime ideals and maximal ideals. Yeah. I think I was careful to say that these ideals have to be proper. They can't be the whole ring. So we study and perhaps generalize the fundamental theorem of arithmetic. Okay, so yeah, let's see. Let R be an integral domain, and I'll explain briefly this. In fact, I'll just come out and say it. In this chapter, my rings will always be commuted with identity. And I will usually be talking about integral domains, right? So I don't want non-zero zero functions because this stuff gets really in the weeds if you allow zero divisors. So number one, a non-zero, non-unit. So what? An element that is neither zero nor is it a unit, pi and r is irreducible if whenever you can factor this generalizes probably a first definition of what you heard for prime integer in the old days, right? A prime integer was one whose only factors are itself and one, right? This is what it means to be an irreducible. This is the standard generalization. What it means is it's irreducible. Whenever you try to factor it, one of those pieces has to essentially be one, right? It's a unit. Two, a non-unit, P and R is prime if P divides AB How many of you have seen this definition for a prime? If you divide the product of two things, it has to divide one of those pieces.
I think I have seen that before in like introduction to proof.
Maybe. And you can prove that these two definitions are equivalent in the integers, but they are not equivalent everywhere. It's a little weird. Notice I did not put the qualifier that P has to be non-zero, because in an integral domain, P is prime. It's just not very useful when you're talking about factorization, because once you got a factor of zero, it's dead, right? However, if you are thinking only about non-zero non-units, this one implies this one, and the converse is not true in general. So let me give you some examples.
Which one implies which one?
Prime implies non-zero plus prime implies irreducible.
So
Okay, so okay, let's look at polynomials with coefficients in Z. This is actually an example. This actually is an example of a ring that actually does have fundamental theorem of arithmetic. Any polynomial with coefficients in Z, you can break it down into uniquely into a product of prime polynomials. 2, 1 plus x, 2 plus 6x plus 20x squared x cubed, or what? Oops. Irreducible. These are examples of things that are all irreducible. Uh, actually, it turns out in C power x, 2 is still irreducible as well. So like it is in the polynomial ring. Can anybody give me an argument why this one is irreducible in the power series ring? Let's pretend that you could multiply this into 2 power series, right? Suppose you could break this up into 2 power series. I don't know much, but I gotta have constant, right?
Probably 2 and 1.
I could change the sign on that, but essentially he's got it, right? It has to be 2 and 1, right? Everybody agree with that?
Yep.
And what does that mean? What's true about the power series that begins with a 1? It's a unit. So no matter how you try to break this up, one of the factors has to be a unit, right? So this is actually, it's funny because it's probably easier to see that 2 is irreducible in ZX, but it's easier to see if this one's irreducible in the power series. The fact that this is irreducible in ZX requires a little bit of thought. How do you know it doesn't factor? Or 1 plus x is a unit.
I don't think we know why it was a unit. I think you kind of explain like, that 1 plus x, most times like 1 minus x squared minus,
In this example, all irreducibles are prime as well. And I'm not going to prove that because I'm going to give you a result that after we've developed some of this stuff, it'll come together easier than I could prove it here from scratch. I'll give you another example. And this, see if you can fool around with this. And justify this. This is the set of A plus B brackets -5 for A and B. This is the set of complex numbers of this form. A plus B times the square root of -5. In this ring, and I think you actually proved this on your last homework, 2, 3, and 1 plus or minus square root -5 are all irreducible, but not constant. There's an interesting exercise where you go through the last homework. You build a machine called Norm that helps you prove this. Let me point out that in this ring, so I'll give you another one here. 7, yeah, 36 points. Yes. This ring doesn't have just irreducibles in it. If you look at this element, it is both irreducible and prime in this ring. Let me give you a really good, here's an example. This is an even better example because you could prove all this crap that I've got written down here using material on the last homework. You can use this to show this. But I want to give you an example where it's easy to see, easier to see, to distinguish between irreducible and prime. I'm going to consider a ring that is almost a polynomial ring. I'm going to call this f x squared x cubed. That's the standard notation for it. And what do I mean by this? These are all polynomials that in a certain sense are missing the linear term. So elements, here look for it. So this is a collection. This is the collection of polynomials that are kind of crippled in the sense that they have zero for their linear term always. What happens when you take two polynomials that are missing the linear term and you add them up? You get a new polynomial range still with a zero linear term. What happens if you multiply two animals like this?
Still no linear term.
That's right, still no linear term because the smallest positive degree term you have is 2. There's no way you can multiply degree 2 by degree 0 and get a degree 1, right? Everybody okay with it? This is actually an integral domain. And I'm going to use degrees to do this. Note, the element x squared and x cubed are both irreducible. You can't reduce them anymore. And let me argue this a little bit. Let's suppose that you could reduce x squared. Suppose you can find. What is the degree of x squared? Just naked x squared by itself. What's the degree of that? 2. Now, what we know about degrees so far, what are my choices for the degree of the factors of x squared?
2 and 0.
Right. Well, I'm going to argue more naively than that. 1 and 1 is not possible.
Yeah.
Right? Because there is no degree 1 term at all, right? So these can't be a degree 1. So your only choice left is degree 2 and degree 0, and vice versa. And what is true about degree 0 polynomial? They are non-zero constants, which are
units.
Right. So x squared, irreducible. X cubed, this was just a little bit more complicated, but it's the same, it's essentially the same thing. You can either have degree 3, 0, or 2, 1. And you can't have the degree 1. Everybody with me so far? So here, these are both irreducible elements. Okay, so far we're good. Now, check this out. So this is you see immediately this ring does not have the fundamental theorem of arithmetic because x to the 6 factors into 3 irreducibles this way, 2 irreducibles that way. So not only do you have different factorizations, they're even of different lengths. Notice that in this example, x squared divides x cubed times x cubed. Everybody agree with that? X squared has to divide x6, product of x cubed. But x squared does not divide x cubed. Because there would have to be a quotient that is a degree 1. All right. So also x cubed divides x squared x4, but x cubed does not divide x squared x cubed does not divide x4. So x squared and x cubed are irreducible, but not prime. And that example, I think, is easy to see. Just using this degree chart. Okay, Any questions on that? Okay, so let me give you following lemma. Let R be an integral domain and X non-unit. And then X is a prime ideal, or I'm sorry. So this is kind of a nifty little result. This is how you tell an almost prime. Just look at the ideal generated by its prime ideal. Proof. Let's suppose first that suppose that X is a prime ideal, and suppose that it divides A times B. This implies XR equals AB. Therefore, AB is the ideal generated by X. Since the ideal generated by X is prime, X and A, I'm sorry, A is an X for the therefore, if A is an X, then A equals XY, so Y R, and X is a group somewhere that happens to be B is an X. And I will let you prove the other direction because it's essentially exactly analogous to this. Any questions? Questions before we break for the joyous holidays? All right, I hope you all have Thanksgiving, or have a very nice Thanksgiving, safe travels, and we will see you at least by Monday.